Hello, fourth grade teachers. Today we're going to look at Unit 5, Building Conceptual Understanding of Angle Measurement. The purpose of this video is to provide an overview of the standards, suggested pacing, and sample some instructional strategies. In this portion of the video, we're going to review the AKS and Indicators of Achievement, or IOAs, for Unit 5. The AKS is the overarching knowledge and skills that students are expected to master. The IOAs are the learning objectives that allow students to demonstrate mastery of the AKS. The AKS and IOAs may not be taught in their entirety the first time they appear on the instructional calendar. Some AKS and IOAs will appear multiple times throughout the year. In Chapter 2 of the video, we will look to see how the AKS and IOAs in this unit are paced in more detail. Unit 5 has one AKS. Under the AKS, you will find the Indicators of Achievement, or IOAs. In Unit 5, you will teach all of the IOAs for AKS 4MA.E.7. Students extend the measurement reasoning they have previously developed by exploring angles as an attribute to shapes. Students recognize angles as geometric shapes formed when two rays share a common endpoint. Students draw right, acute, and obtuse angles based on the relationship of the angle measure to 90 degrees. Students build conceptual understanding of angle measurement by investigating angles within circles and using non-standard units of measurement by iterating wedges. Angle measurement should be introduced with non-standard tools such as pattern blocks, unit angles, and/or wedges prior to introducing protractors. As students in fourth grade begin to make sense of how to iterate wedges to measure angles, the idea of the degree can be introduced as a standard wedge to iterate for precise and common or standard measurements. Using 360-degree protractors, using 360-degree protractors make an explicit connection to the degrees of a circle and build conceptual understanding of angles. Students will transfer their understanding that a 360-degree rotation about a point makes a complete circle. Students explore the concept of degrees using a 360-degree protractor and determine an angle's measurement through problem solving using multiplication, a missing factor problem, or division, understanding that a circle is 360 degrees. It is important that students have experience with a 360-degree protractor prior to using a 180-degree protractor, which tends to be more abstract. However, it is not necessary for students to use a 180-degree protractor. Students at this grade level should determine an angle's measure through problem solving using multiplication or division and the fact that a circle has 360 degrees. Clocks are also a great tool to use as students explore angles. A student may reason that there are 12 wedges in the clock circle by thinking about the hour hand at each number. If I know that a circle has 360 degrees, then each angle wedge from the center of the clock measures 360 divided by 12, or 30. So the measure of each wedge in the clock is 30 degrees. Notice the extension IOA 7C. Extension IOAs support the differentiated needs for your students. As you can see, the word extension is bolded and in parentheses to notify that these are extensions and are specific to Gwinnett County. Please note, you will not find resources from the state of Georgia for these IOAs. As a reminder, the state coding is listed with each GCPS IOA, so you can find resources on the Georgia DOE website. We're going to talk about IOA 7A. In fourth grade, students recognize that angles are created when two rays share a common endpoint or vertex. Students classify and draw angles using a variety of tools. They will determine if the angles are acute, right, or obtuse based on the relationship of the angle measurement to 90 degrees or using a known right angle. Angles are geometric shapes composed of two rays that are infinite in length. Students can create paper rotating protractors to help them understand this concept. As the paper protractor is rotated or turned, the size of the angle is seen to get larger. Students describe the type of angles in terms of their relationship to right angles. Students describe acute angles as less than the measure of a right angle, or 90 degrees. Students describe obtuse angles as greater than the measure of a right angle, or 90 degrees, but less than a straight line or straight angle. Students draw representations of each type of angle and are able to identify angles in two-dimensional figures. Students often confuse angles when the orientation is different than what they might have seen previously. Allow opportunities for students to see angles as two rays, angles in shapes, and angles in our natural environment. Students at this grade level are not expected to know that straight lines represent 180-degree angles. For IOA 7B, students investigate angle measurements within circles using non-standard units, wedges of a circle, to make sense of how angles are measured. Angle measurements are introduced with non-standard tools such as pattern blocks, unit angles, and/or wedges prior to introducing protractors. 360-degree protractors support an explicit connection to the degrees of a circle and build conceptual understanding of angles. Students understand that a 1-degree angle is one in which the angle turns through the circle with an arc that is 1/360th of a circle. Students represent angle measures using the degree symbol and determine an angle's measure through problem solving using multiplication or division and the fact that a circle has 360 degrees. For example, students could place 6 green triangles, pattern block triangles, around the center of a circle. Since there are 360 degrees in a circle, you could find the angle measurement of the triangle by dividing 360 divided by 6. And so that would show that each triangle has a 60-degree angle. It is important that students have multiple experiences with a 360-degree protractor prior to using a 180-degree protractor. Please note again that students are not required to use a 180-degree protractor in fourth grade. The protractor is one of the most poorly understood measuring instruments. Part of the difficulty arises because the units or degrees are so small, and also because the numbers on a protractor run clockwise and counterclockwise along the edge. This makes the scale hard to interpret without a strong conceptual foundation. Students at this grade level are also not expected to know that straight lines represent 180-degree angles. For extension IOA 7C, this extension IOA allows for the natural integration of math practices number 3, which states that students must construct viable arguments and critique the reasoning of others. Guiding questions to evaluate the student's performance may be used to reflect on students' critique of classmates' reasonings after analysis of the scenario. Students should also be able to identify a list of questions to ask peers. In Chapter 2, we will be discussing our Unit 5 pacing. Our pacing guides are closely aligned with the state pacing to ensure we are following the expectations from the state. The pacing guide is an example intended to model how instruction of the AKS and IOAs in each unit may be facilitated. But teachers should design pacing to be responsive to the learning needs of their students. Here's a quick glance at our vertical progression. Most of the items on this vertical progression are the geometric concepts that fourth graders are going to be learning in our next unit, Unit 6. But I do want to point out, prior to fourth grade, you can see in that second bullet that third graders identified right angles and the presence or absence of them in quadrilaterals. And then after fourth grade, fifth graders are going to be classifying polygons based on geometric properties. Fourth grade is the grade level where angle measurements are taken for the first time. So now let's look at our pacing guide. The suggested length for Unit 5 is 3 weeks. Unit 5 focuses on AKS 4MAE7, investigate the concept of angles and angle measurement to estimate and measure angles. So let's start by looking at our first day. Let's start by looking at our first day here for 7A. The suggested sequence is located on the left side of the pacing guide. The left column provides the learning progression for the AKS and the IOA, showing whether it is concrete, representational, abstract. The bulleted list states the learning objectives within the IOAs, as well as any suggested manipulatives. The resources for each day are located on the right side of the pacing guide. Resources include traditional lesson plans, task-based lessons, formative assessments, small group instructional moves, student tasks, and any additional resources that are aligned to the learning targets for that day. Also embedded in the pacing guide is suggested resources to use from our textbook adoption, Georgia Reveal. Georgia Reveal is an adopted resource. However, it is not your main and only resource. You will find Georgia Reveal adapted lessons aligned to the intended learning targets, as well as other resources on your pacing guide. These are just a few of the Georgia Reveal resources available. Please go to your employee portal to access all of the Georgia Reveal resources available to best meet the needs of your students. So, Unit 5 starts with 7A. It is concrete representational. Let's just kind of read through these bullets. We're going to see that first, we're going to just recognize that angles are formed when two rays share a common endpoint. Students will identify and recognize right, acute, and obtuse angles, all based on their relationship of the angle measurement to 90 degrees. They will not be measuring angles at this point. And you can see the manipulatives suggested: anglegs, color tiles, fraction circles. And these fraction circles are really nice to use as wedges. So we won't really using the fraction part of them, but just the wedge part of them. You can also see that it starts out with a task-based learning day here. So that's how we're starting. And we have 2 days of 7A. Oh, notice that on days with task-based lessons, we have labeled it differently to indicate that it is a task-based learning day, not a teacher-directed lesson. There are 4 task-based lessons throughout Unit 5. In IOA 7A, there are 2 suggested pacing days on the pacing guide. Students will first learn how to recognize whether an angle is right, acute, or obtuse based on the relationship of the angle measure to 90 degrees. And again, they're not measuring angles yet. We build the conceptual understanding of that first. After a couple of days of IOA 7A by itself, we begin to cluster 7A and 7B. You can see that now we are representational. There are 2 days where 7A and 7B are clustered. On these 2 days, students are still recognizing the type of angles, but using wedges in a circle to begin referencing 360 degrees of a circle with the center at the common endpoint of 2 rays. Then you can see we have another concrete day where they're discovering degrees with wedges and pattern blocks. We're still thinking about non-standard units, wedges of a circle, before we get into standard units. So you'll see with our bullets that we start with non-standard before you'll start to, I'll point out when we start to use degrees. So now we're into 7B, IOA 7B. The suggested pacing for IOA 7B is 9 days. We will begin 7B with using non-standard units, and again, we'll move into the standard units. The Georgia DOE prefers that students use 360-degree protractors so students understand that an angle measurement always relates to a circle having 360 degrees. I'm going to scroll on down until we see, so we can see on this day that's concrete representational, the first bullet here, measure angles using standard units. And we have some suggested manipulatives here, starting out with the 360 paper protractor that we referenced earlier. After that, students will begin measuring angles using a 360-degree protractor. I'm going to scroll down to where we see that. So we're still with the paper protractor there. And then another thing that students will need to do is they will use division or multiplication to determine an angle measurement. For example, they would, this right here is talking about recognizing that an angle is a fraction of a 360-degree circle, and they can find that angle using division or multiplication. Another thing we would like to point out is that students will write an angle measurement with degrees, but also as a fraction. So for example, we could write the angle measurement as 45 degrees, or they could write it as 45 over 360 degrees, or 45 360ths, to make that reference to the 360 degrees of a circle. So we're writing it with degrees and as a fraction. Let's keep scrolling down. You can see this lesson here, measure angles using a 360-degree protractor with the standard units. We have a few days of that. Here is a lesson where you're using division to determine the angle measurement, or they could find the missing factor of a multiplication equation. You can see that there's some more task-based lessons. And then I want to point out that the very last day, we have a lesson where students can use a 180-degree protractor. But again, you can see the note that Georgia states that students can, but are not expected to use a 180-degree protractor. We did want to have 1 day of that so that students were exposed to a 180-degree protractor. Looking to see if there's any Georgia DOE tasks to point out here. Here's one right here. Sometimes you will see some Georgia DOE tasks like this check for understanding formative that are linked directly onto your pacing guide. We just always like to remind you that when you open a Georgia DOE task on pacing, it is going to open a document with multiple resources. The link provided will land on the first page of the task that corresponds with the page number noted on the pacing guide. So for instance, this one, when I click this link, it should go directly to page 1. But if I am going to this Georgia DOE task, the paper protractor task, when I click this link, it should open up to page 4. And you see that this task has a range from page 4 to 7. Similar to your GCPS resources, this is a live document and that could be updated by the state at any time. So that's why we have left these as links directly to the state document. All right, scrolling down to the end of our unit. At the end of the unit, you have your suggested Unit 5 summative assessment. In Chapter 3, this portion of the video will sample specific instructional strategies that will be utilized in this unit. Please refer to the Analyzing the Standards, sometimes referred to as the ATS, for guidance on additional instructional strategies for each IOA. In mathematics, the emphasis is on reasoning and thinking about the quantities within mathematical context. Specific strategies for teaching and learning are not mandated by the Georgia Department of Education or assessed on state or federally mandated tests. Students may solve problems in different ways and have the flexibility to choose a mathematical strategy that allows them to make sense of and strategically solve problems using efficient methods that they are most comfortable with and that make sense to them. It is critical that teachers and parents remain partners to help each child grow to become a mathematically literate citizen. These standards preserve and affirm local control and flexibility.
Today, we're going to investigate how students can recognize angles as geometric shapes formed when two rays share a common endpoint. We'll also look at how students can draw right, acute, and obtuse angles based on the relationship of the angle measure to 90 degrees. Right? So what do students need to be able to know, understand, and be able to do? In fourth grade, students recognize that angles are created when two rays share a common endpoint. Okay, so students can create angles with geosticks by hooking together two geosticks as two rays to create an angle. And the common endpoint would be where those two rays meet. Okay. All right. Students will also determine if angles are acute, right, or obtuse based on the relationship of the angle measurement to 90 degrees or using a known right angle. All right. So let's take a minute to think about how students can classify and draw angles using some different tools. All right. All right, so here is a map that I created. Your students can create these with you as they begin to explore angles. This is just a regular piece of white copy paper. I folded it vertically and I folded it horizontally so that there were 4 fourths that were created from these two perpendicular lines, okay? So these two perpendicular lines created 4 90-degree angles. And I traced on the creases or the folds to show those 4 90-degree angles. And I know they are 90-degree angles because when I use a square and place a square on each of these angles, It is exactly 90 degrees for each of these angles. So the two sides of each of these squares form 90-degree angles. And they called those square angles in third grade. Okay. Now, thinking about these 90-degree angles, okay, we can look at some other pattern block shapes. So what if the shape was a triangle? Okay. If I line up one side of the triangle with this horizontal line, I can see this vertical perpendicular 90-degree angle here. I can see that that triangle angle is less than the right angle, or less than 90 degrees. And I can also see it by placing that pattern block on top of that square. It is less than a 90-degree angle. Okay. Thinking about the rhombus, this particular angle in the rhombus that's formed by these two sides of the rhombus and lining up the vertex with the center of those perpendicular lines, I can see that that angle is also an acute angle. It is less than 90 degrees. If I turn the rhombus a different orientation and line up a different side with that horizontal line and place the vertex of that angle at the center of the perpendicular lines, I can see that this shape, or sorry, that this angle in particular is now an obtuse angle. So using this visual representation, I can see that the rhombus has at least one obtuse angle and one acute, right? And we could look at all of the angles in these shapes, okay? All right, another great tool to use are fraction circles, okay? This circle was created by tracing this whole fraction circle, right? And when I place the 1/4 fraction circle on this work mat, I can see the two rays that form that wedge, or that 1/4 piece, is exactly 90 degrees. It's a right angle. Okay. This is the 1/8 fraction piece. Again, I lined up one side of the fraction piece with the horizontal line. That's the vertex of my angle. Students could actually trace these angles if they would like. Okay, they could trace the sides of those fraction pieces to show the angle. And I can see that that angle is less than 90 degrees. It is less than a right angle, so it is acute. Okay. And this is the 1/3 piece. It's turning from this horizontal line. This angle is turning from this horizontal line over beyond past the 90-degree or right angle mark. So this angle is obtuse. It is greater than a right angle, greater than 90 degrees. And I can see that again, just stacking my fraction pieces. I can see it's greater, right? So there's lots of great tools that students can use to help them think about angle measurements and the size of angles. Okay. Another tool that students can use is the clock in the classroom, or their Judy clocks, their manipulatives. So using, again, these geosticks, we can create a right angle at the 12 o'clock hour and the 3 o'clock hour. Okay. We could also rotate those rays and show a right angle at the 3 o'clock and 6 o'clock hours. We could create an acute angle. And what's great about geosticks and clocks is that students can see the angles in different orientations. Okay. All right, so these are just some different ways that students can think about acute, right, and obtuse angles and recognize and identify them and describe them using pattern blocks, fraction circles, and clock faces. Okay. Another way students can experiment with angles is just using pictures of angles. So here are some different pictures of angles. There's about 16 of them, I think. But these pictures of these angles can be turned in different directions, and students can sort them by acute, right, and obtuse. And they can also describe and explain why they are acute, right, and obtuse. So, for example, angle F is a right angle. I can check it with a pattern block and see that it is a 90-degree angle. Or I could just use another known angle, such as a Post-it note or an index card. So it will fit exactly there. Okay. This angle, angle H, if I turn it just to whatever direction works for me, I can see that that angle is less than a 90-degree or right angle. So it would be acute. All right. So these cards are a great way for students to think about how the two rays of the angle form different types of angles, and they can describe their angle measurement related to a 90-degree angle or a known right angle. Okay. Another thing that students can do is they can think about shapes and the types of angles that are in shapes. So here is a task where students can sort shapes based on the types of angles that are in those shapes. So for example, card number 10 is a triangle. Okay. And I can use a known right angle to compare the angles to. So I can see that this angle in the shape is a right angle, where this angle over here on the other side is acute. This is also an acute angle. So I can see that this triangle has two acute angles and one right angle. Okay, so I would sort number 10 in that category, right? So this task would require students to really observe and evaluate the types of angles that are in different shapes and then sort them based on right and obtuse, acute and obtuse, acute and right, or just only obtuse angles. So like this number 7 would be only obtuse angles. That octagon. This one would be only right angles. Number 4, the rectangle. So there's a lot of conversations that students can have about these shapes, okay, and the types of angles that are embedded in them. All right. Last, students might be given a scenario, an abstract scenario, where they are trying to demonstrate their knowledge of angles, where they're going to show that they know which angles are right, acute, and obtuse, as well as describe them and draw them. All right. So in this particular scenario, it says Mr. Rodriguez designed a toy train for his grandson. The toy train has at least one acute angle at least one right angle, and at least one obtuse angle. What could the toy train look like? Sketch Mr. Rodriguez's toy train design and label each type of angle. All right, so this particular task is asking students to design a toy train. So students will draw a toy train using straight lines. They could use some curved lines too, all right? But they want to be able to label each type of angle that is formed by those straight lines, which would be the rays of the angle. So let's say the student created this design of a toy train. Okay. Once they design the toy train, they're going to label each type of angle. So the student would look at the different angles and identify them. So here is a right angle. Okay. Over in this area of the train is an obtuse angle. It is greater than 90 degrees. And I can test these angles. I can place my known right angle to test that that is a right angle and that is an obtuse angle. It is definitely greater than a right angle or 90 degrees. Okay. I also see an acute angle in this part of the train. Okay. So students can create their own pictures and designs and then find and describe the angles. All right. So today we looked at how students can recognize angles as geometric shapes formed when two rays share a common endpoint. And we also looked at how students can draw right, acute, and obtuse angles based on the relationship of the angle measure to 90 degrees. So students are using that 90-degree angle as a benchmark, all right? And they used fraction circles. Students can use pattern blocks. Students can use geosticks, clock faces. There's all kinds of materials that they can use to help them understand the different classifications of angles and how to draw them. Today, we're going to dig into IOA 7B, measure angles in reference to a circle with the center at the common endpoint of two rays. Students will determine an angle's measure in relation to the 360 degrees in a circle through division or as a missing factor problem. All right. So in this IOA, students will investigate angle measurement within circles using non-standard units or wedges to make sense of how angles are measured. Angle measurements are introduced with non-standard tools such as pattern blocks, unit angles, or wedges prior to introducing the actual protractor tool. Okay, so what could this look like in your classroom? All right, so we're going to begin with our visual from IOA 7A. And we know that when we turn 4 90-degree angles around a circle, it will make a complete full rotation of 360 degrees. So I can turn 90 plus 90 plus 90 plus 90, and it will be a complete full rotation of 360 degrees. So thinking about that, I know that 360 degrees divided into 4 equal-sized fractional wedges is equal to 90 degrees. And I know that 4 90-degree angles, or 90 degrees times 4, will make a complete 360-degree circular rotation. Right? So thinking about that, we can engage our students in a task. It looks like this on our pacing guide, but the students can actually just explore and collaborate with their peers about how to figure out the measurement of different angles of pattern blocks, thinking about the 360 degrees in a circle. So we know the squares have 4 right angles. So all of those angles would be 90 degrees. Okay. But what about if we had hexagons? If we place hexagons around the center of this circle, we can see that there are 3 rotations that are the same exact fractional amount. Right? I can see there are 3 rotations. So I know that 360 degrees divided by 3 will give me an angle measurement of 120 degrees. So this one angle measure here with these 2 sides as the 2 rays, it's equal to 120 degrees. And I know that 3 120-degree angles, or 3 times 120, is equal to 360 degrees. Right? We can turn these shapes and just see that really they're all 120-degree angles, because this hexagon is a regular figure like a square. All right. So what about the triangles? Well, if we place the triangles around the center of the circle, I can see there are 6 turns around this circle that are the same distance or same measurement, because each of those triangles is a fractional wedge of the circle. And also notice that all of these wedges are the exact same size. They don't overlap. They're not spread apart. They are touching just like you would tile finding area. Okay. Now, same thing if I take a 360-degree circle and divide it into 6 equal-sized rotations. I can solve the math problem. 360 degrees divided by 6, that will give me 60 degrees. So I know that this angle here in the center of the circle is 60 degrees. And 6 60-degree angles, or 6 times 60, is equal to 360. Okay. Now, as students explore with these pattern blocks, okay, they'll begin to think about benchmark angles and just the relative size of these angles. All right. The same work can be accomplished with fraction circles, just like we saw in 7A. So we can go back and do that great work and see that this is 3 equal-sized wedges that compose the full 360 degrees of that circle. Okay, so again, I know that 360 divided by 3 is 120 degrees. So I can figure out, using division or multiplication with an unknown factor, that there are 3 120-degree angles that make this full circle. Okay. All right. So again, pattern blocks and fraction circles can be used to discover these measurements using division and multiplication. Right. As students work with these materials, they can also create their own circular protractor that's not marked, but they can start estimating and thinking about the size of angles. So this is made with 2 circles that are cut out. So students can cut out 2 different colored circles, and they each have a cut from the arc of the circle to the center, right? And when you slide them together, it makes a circle that you can rotate, right? So here I can create a 90-degree angle. And I can check that using my known right angle. Get straight. This There it is. And if I turn it again, I will have 90 plus 90, which is 180, and so on. All right. So students can begin estimating angles. So if I know this is 90, then I know half of 90 would be 45. And so we're just going to kind of begin thinking about those benchmark angles and estimating angle measurements. All right. This can also be discovered further by students by actually using circles with the partitions already in them, okay? So here are two circles that have been partitioned into eighths, all right? And students can also make a circular protractor with these, or they can use them just to find the measurement of different angle wedges. All right, so for example, I can put a square here, okay, and I know a square turns around two of these equal-sized wedges. All right, well, I know that there are 8 wedges. All right, so again, if it's 360 divided by 8, I know that each of those wedges is 45 degrees. Or I can just think about that 90-degree angle. 90 divided by 2 is 45 degrees. Okay. Same thing with the other pattern blocks. So on this one, I don't have an exact measurement, but I can see that that angle is not quite to this ray here. So if I start on this baseline, I can see this is 45, this is 90, but it's not another full 45. So this is not 135 degrees quite yet. It is 120, but the students can estimate it's between 90 and 135. All right, so it's maybe about 120. Okay, so there's lots of ways partition circles can help. Again, if you turn one of these over face down, you can link them together like this and do the same work. You can make angles. So we have the 90-degree angle, 45-degree angle, 135-degree angle, or 45 plus 45 plus 45, right? So that's an angle with 8s, or a circle with 8s. You could do the same work with 12ths. And 12ths is related to the clock because there's 12 hours on the clock. So 12ths is good to use with pattern blocks and fraction pieces. So if I place, let's say, that piece here, okay, I can see that this orange pattern block piece, which is 1/6 of the circle, is made up of these two wedges. Now the wedges are smaller than the 8ths. But that's okay. We're going to figure out what each of these wedges angle measurements are. So if I know that there are 3 wedges in 90 degrees, I know that 90 divided by 3 is 30 degrees. And 3 of these 30-degree wedges would be 90 degrees. Or I could just divide 360 divided by 12 to figure out 30 degrees. All right. But we want students to still continue to use that 90-degree angle as a benchmark in their thinking. Okay. All right. So if we know each angle is 30 degrees, then we know that this angle would have a value of 60 degrees. All right. This third would still have a value of 120 degrees, right? So as you allow your students to concretely figure out and problem solve the measure of angles using these materials and different representations, it will help them understand and solidify those benchmark angles and just the measurement of those angles and how to figure them out, right? All right, so Another task that students can engage in is similar to the task with just the circle and the pattern blocks. Students can, just like we did here, figure out the measure of each wedge, and then they can tell, is that angle, is it acute, obtuse, or right? So let's say it was the triangle, okay? They could say that that is an acute angle. It is 2 wedges. Each wedge is 30 degrees, so the measurement would be 60 degrees of that triangle pattern block, right? Okay. The Georgia DOE also has a good task. Okay, where students can cut out some wedges. Looks a little like this. See. Okay, so I cut out the wedges here. Right. So it's 1 page, and the students are cutting out these wedges, and the wedges, just for your reference, are the same as a 12th. They're the same size if you want your students to use the 12th fraction tiles, but they are basically building, tiling these wedges inside these angles to figure out their measurements. So they have to figure out that each of those wedges is 30 degrees to know the actual measurement. Okay. Some of your students may just say it's 2 wedges. Others may say it's 2 wedges and it's 60 degrees. So we want our kids to be having those conversations with each other and trying to figure out the actual angle measurement with wedges. All right. All right. So that's wedges in a circle. Another DOE task that is fun is this one, where the students are exploring wedges again, and they are estimating a measurement. I'm sorry, they are measuring the actual measurement with these wedges, and they're putting their measurement, and their partner is writing their measurement, and they're trying to see who is correct and do they agree on that measurement. So they're recording the measure of each angle. Okay. So again, that's using a different size wedge. This one's using 8s, where the other one was using 12. So the size of the wedge does not matter. We just want our kids to understand that they're measuring circles using wedges. Okay. Students can also use blocks. All right. So just like in IOA 7A, okay, a clock is a great way to help kids figure out angle measurements. All right, on this particular clock, when we fold it horizontally and vertically, we can discover where those rays of the angles are on the clock, where the creases are, right? So this clock has 4 90-degree angles, right? And just like the circle with the 12 twelfths, the clock is designed the same way. So students can create angles, and if they can figure out the angle measure of each hour, then they can really figure out the measure of any angle on that clock using the clock hands to help them build the angle as the rays. Okay, so we know already from our experiences that each of these angle measures in this circle are 30 degrees. We're going to make 12 30-degree turns around this clock to create 360 degrees. Right? That's what we had figured out with the concrete materials. So I know that at 1 o'clock, that would be a 30-degree angle. If I turned my rays or my hands on my clock to the 1 and the 4, I can see 1, 2, 3 wedges. So that would be 90 degrees. It's a different orientation for 90 degrees, but it's still 90 degrees. All right. Okay, and so moving from there, we can also use some pictorial representations. Right? We can actually have our kiddos create their own protractor by cutting out 2 paper protractors, flip one face down, cut them from the arc to the center, and when we place them together, we can create angles of different sizes, right? So right here we go. All right, so put this together for you. All right, so here is the 90-degree angle. We're going to start at 0. And so here we can talk to our students about how to read a protractor. We want to start at 0 and count all the way around, counting on to 90. All right. Please remember that using the actual degrees of a protractor is where we go last. It is going to be the actual measuring of the degrees, and it will be easier for them to understand if they have worked with all the different kinds of wedges and understand that each of these tick marks is a 1-degree turn of this circle. And so that angle is formed by one ray moving around the circle and turning around the circle to create that angle measure. All right. There is a task where students, again, can use fraction tiles, and they're figuring out like a half of a circle is 180 360th of a circle. And in degrees, it would be 180 degrees. So we're learning how to write that measurement as a fraction and as degrees. Okay. Right. So the third of the circle would be 3/3, or they could just place one on the protractor. They will see it has a measure of 120 degrees. Okay. So it would be 120 360ths of the circle, or 120 degrees. So notice that, again, that we've gone from wedges to the actual standard measurement, all right? And again, students can practice creating angles of specific measurements using an actual paper protractor and also using the actual protractor tool, all right? All right, so last, the abstract version of this IOA is problem solving, where students are trying to just figure out from a problem the measures of angles in a circle. All right, so this problem says Lana has a circular apple pie. The pie will be shared evenly between 8 people. What will be the angle measure of one slice of pie? And justify your answer. Okay, so when students get to the abstract, we're hoping that they can use some mathematics without the concrete materials to help them figure this out. All right, so what we're hoping a student will see is that there are 8 slices in this apple pie. Okay, and I can see in this 90-degree angle, there are 2 slices, all right? And I know that 90 degrees divided by 2 is 45 degrees. And I also know that 2 45-degree angles is 90 degrees, all right? So I know that each of these angles, as it turns around the circle, each one is exactly 45 degrees, okay? I could also think about the whole circle. if there are 8 slices of pie in a full circular rotation of 360 degrees, we can figure out 360 degrees divided by 8, which is also 45 degrees. So it takes 8 45-degree turns to make a 360-degree circle. Okay. All right. So I also know then if someone ate 3 slices of pie, that would be 45 times 3, or 45 plus 45 plus 45, which is 135 degrees. So I could figure out all kinds of things with this pie problem once I figure out the measure of one angle. Okay. But the measure of one slice of pie is 45 degrees. And I know that because I figured it out using division. 360 degrees divided by 8 equal fractional pieces is 45 degrees. All right. So today we looked at how students can use non-standard units like wedges, pattern blocks, fraction circles, and connect it to the 360-degree protractor to support that explicit connection to the degrees in a circle and actually measuring angles. All right. We want to build that conceptual understanding of angles using these materials and allowing students to look at those turns that the angles are making around the circle. All right. So just remember that we want our kids to also note that there is a fractional amount. So like each of these pieces would be 45 360ths of the circle. All right. But it was asking for the angle measure for that particular problem. So that's why we wrote that as 45 degrees. Okay. All right. So enjoy figuring out angles. And remember to follow that concrete representational abstract progression.